So good evening, ladies and gentlemen, and welcome and thank you for coming tonight. This is fantastic in this new building, but it's sometimes these theatres make it very difficult to know where to look, where to stand. So I'll just sort of wander around a little bit as if I'm really comfortable with this, and it'll give Colleen a chance to go, I'm not going to do that when I'm talking. So thank you very much for coming tonight, and I'll introduce Colleen in a moment, but the first thing that's most important, of course, is acknowledgement of country. So I'd like to begin by acknowledging the traditional owners and custodians of the land on which we meet today, the Wurundjeri people of the Kulin Nation, and we pay our respects to elders past and present. Now, on the table in front of you, and I'm following my instructions here that I've been given, you are on a table that's also a whiteboard, and there should be a texter, a whiteboard texter there. Now, don't get too excited. If you were to be writing on the walls out there, we would be photographing and putting them up and spreading them all around the place. You're only on a whiteboard. Yours won't be saved and put anywhere. And Colleen has made very clear that you are not to be playing noughts and crosses while she's presenting tonight, but the idea is that any questions, issues or ideas you get as a consequence of the lecture and during the lecture, of course, that you write them down so that at the end you're not making up questions willy-nilly because you want to make sure you've got something to say. You've actually thought it through carefully and you've actually been scribbling notes to yourself as the lecture progresses. And hopefully that will create a strong sense of recognition in your mind of what it was that triggered that question and what it is that you want Colleen to explain more about at the end. So it's an aide de memoire. How's that? And you use the table to write that on. And the one last thing is that we would like you to leave the appropriate questions on the table, rub out any of the other stuff, because we may very well come around and photograph those and add them to the way that we put this presentation online when we finish. And speaking of online, it is always fantastic to have real people live in a place, and in this day and age that is a big deal when you think about how things are available everywhere all of the time. And so it is fantastic to have you here, and that is important. But there are over 50 people that are live streaming this at the moment, and as you can see from the cameras, we do save this and put it online, and it is another way of making the presentation available and able to be used in different ways. So now let me turn to Colleen. And how lucky are we to have Professor Colleen Vale at Monash University. She comes with a huge reputation, not just for her ability in maths education, but also for her ability to mentor, support and encourage staff to grow in their understanding, their teaching, their learning and their research. And so in a Monash sort of way, Colleen's found her way back to where things started. And we are so very happy to have her back here. You would know, anyone who knows Colleen, she's had a wonderful impact on this place in the short time that she's been back with us. Her work in maths education is outstanding. Her work in gender, her ability to actually speak to a topic in an appropriate, strong and powerful way is excellent. And I'm putting her under enormous pressure, you can see as she's going now. Colleen, so grateful to have you back here at Monash, and so fantastic to have you as one of our academic community leaders. Welcome tonight and welcome to the audience. Thank you very much.
Thank you, John. And just to clarify what he means by me being back, I did my undergraduate degree here. I've got a degree, an economics degree, with a major in mathematics and an honours in economic statistics. So I spent a fair bit of time in the Ming Wing, which we're not allowed to call it the Ming Wing anymore, when I was here. And I lived on campus when I first started because I'm from the country originally, so I literally am kind of returning to the beginning of my tertiary experience by being here. Thank you everyone for coming. I'm here to talk about mathematical reasoning and providing opportunities for creative and critical thinking, and I'm really wondering about trying not to make a bit of eye contact with everybody at some point in a lesson without getting too dizzy. So So reasoning is the mathematical thinking that creates and validates mathematical ideas and new knowledge. Students discover and make sense of mathematical ideas and concepts when engaging in reasoning through inquiry-based tasks. What I want to talk about today is where these ideas came from in terms of our research, a bit more about what is reasoning, why is it important, what does reasoning look like in the classroom, what do teachers notice when students reason, what are the pedagogical implications of the work that we've done, and I've got some closing remarks. And throughout this conversation, or my talking really, I hope to illustrate why I think it's connected to this idea about creative and critical thinking, which we know has been in the news in the last couple of days. I'll come back to that. So this work is a result of about working with my colleagues at Deakin University for the last 5 years and starting our work on mathematical reasoning and realising that teachers needed a bit of support with this because they weren't doing it, they didn't quite know how to do it, there was some confusion about what it meant, changes in the curriculum from the VCSF to where reasoning was part of working mathematically, and then we got the Australian curriculum, and you know, as teachers constantly kind of having to deal with changes in the curriculum and shifts in definitions. So we started working on making sense of it for ourselves with teachers, and we conducted demonstration lessons in four Victorian schools and 1 Canadian school, and collected ideas from teachers, evidence from teachers, ideas from students, evidence of students' reasoning. We went on and did some more case studies about how teachers planned for reasoning. And then we got another grant to try and think about how might you assess reasoning in classrooms. So I'm just sort of pulling the main ideas from all of those studies over that time together in the presentation today. So one of the things that we did initially was to interview the primary school teachers in our schools, and we discovered that they had a broad range of ideas. And this was a part of the framework that we put together to help us understand where teachers were on this framework, from thinking through to communicating thinking, problem solving, validating thinking, forming conjectures, using logical arguments for validating conjectures, or making connections about different aspects of mathematics. So these are the words that teachers used with us when they were attempting to describe what they thought reasoning was. And so we were then able to use this framework to track their understanding and thinking about perceptions of reasoning over the time when we were doing these 2 demonstration lessons before, in the middle and after, and collecting their work. And we did notice a shift in their thinking, in their perceptions, from the idea that reasoning was just thinking through to reasoning involving validating thinking or forming conjectures or using logical argument. So that was really good. So go back. It's not surprising that teachers are confused about what reasoning means, because the literature is also pretty confusing about what reasoning means as well. And obviously at the time we were doing our study, Denote and Kieran were also noticing how difficult it was to really tie this idea of mathematical reasoning down. And they discovered that in the literature there was really 2 ways of looking at it. One was what they termed as the structural aspects of reasoning. So some of you might have heard about the idea of inductive reasoning and deductive reasoning and abductive reasoning. And they're kinds of ways in which you might teach reasoning as a topic, where today we're going to do inductive reasoning, and what all the conventions are around doing inductive reasoning, or what all the conventions are around doing deductive reasoning. And there are units of study in tertiary mathematics that are all about those kinds of things. Whereas the other set of literature is really about the process aspects of reasoning, the doing things. What is it that you're really doing? And they noticed 2 main ideas: this idea of searching for similarities and differences, and the idea of validating. Now, this idea of searching for similarities and differences is John Mason. If anybody knows John Mason's work, he's really on about looking for invariance and the search for invariance. If anybody knows James Cappett's work, he's always saying that mathematics is always about generalising. Press the button too. So this searching for similarities and differences is about forming conjectures and generalising. And the validating also connects with a couple of other words that are associated with reasoning of justifying and proving. And it's this process aspect of reasoning that's in the Australian curriculum. So when you read the definition from the Australian curriculum, you see that it's full of verbs, doing words. So that means if we're wanting having our students to be reasoning, they've got to be doing things, and they've got to be analysing, they've got to be generalising, they've got to be justifying, they've got to be explaining. So it's trying to think about this. It's not about them knowing something, it's about them doing something. Somewhere when I point, it works better. Then it jumps 2 slides instead of 1. Okay, so the next bit is, why is reasoning important? So the literature and our work, we've come to realise that it's important because it gives opportunities for students to discover things, discover facts. They can experience the joy of discovering a pattern or sharing it, or discovering a fact, or discovering a relationship, or discovering something else. So I want to show you a video in a minute that illustrates this idea of creative thinking when they're discovering things. So I've just got to do something fancy here, just to show us what this thing can do. So this problem is about a cube. And imagine that you've got a 3 by 3 by 3 cube, and you've got a tin of paint, and you're going to drop the cube in the tin of paint. The cube's made up of all these little cubes inside it. How many of the faces, how many cubes are going to have paint on 3 faces, on 2 faces, on 1 face, on no faces? What about if it was a bigger cube? If it was a 4 by 4 by 4 cube, or a bigger cube again? Can we find a pattern? Can we see a pattern in what's happening with these 1 painted face, 2 painted face, 3 painted faces, and so on? So we'll go back to the slides, please. I've got to turn this off, have I? Can't remember. Yes. And we'll have if you can click onto the video for me.
It would be the one in the middle.
Yeah.
Like, yeah. Mm-hmm. So then if you have n minus 2, so as you can see, like this is the side, so n minus 2. And let's say we shift it down 1, yeah? So everything else will be n minus 2, as in like the dimensions.
Yeah.
Yeah? So then that's why, and then you'd have n minus 2 here, and you'd also have n minus 2 from here to here. So as you can see, if you want an area, you multiply them together, so you square. And then with this 1 in each face, so times 6.
So he's explaining about how many of the cubes will have 1 painted side on them. And you notice that he was pointing at things, and he was, so that idea of gesture was really significant in the way that he used that as well to communicate. And I think as teachers we forget how often we actually use gesture as well. So he's gesturing and he's doing things, and he's saying, well, if it's only going to have one painted face, and he's got a 10 by 10 cube that he's playing with, not a 4 by 4 one here that I have, and he's pointing to the fact, well, you wouldn't be counting these ones here and these ones here and these ones here and these ones here, and that means it's going to be, and he says n minus 1 on this side, and then I've got to take away the one on the other side, so he said it's going to be n minus 2, and then he said I've got 6 sides, so I've got to multiply by that by 6. So then he's recorded that idea in his own way of recording that symbolic relationship. Okay, so let's move on. So this is an illustration of creative thinking because they've identified a pattern, they've come up with a rule themselves, they've been able to communicate that rule to other people in the classroom. Why is reasoning important? Because it deepens students' understanding of mathematics. Carpenter and a few other people who are involved in this work of understanding about reasoning, they say, we found that students who learn to articulate and justify their own mathematical ideas, reason through their own and other mathematical explanations and provide a rationale for their answers, develop a deep understanding that is critical to the future success in mathematics and related fields. So this next task, which we use various versions of, is it true, let's justify. We borrowed this idea from Kazemi and others from the University of Washington. And this is a statement here, 511 minus 34 equals 27. Is it true? Let's justify. And this is an illustration of critical thinking.
Subtract like 511 by 34. There's like one columns of where you have to subtract, and it's columns and there's hundreds of columns. They might have just not carried over, and they just might have just left it like that.
Okay.
And that's what I thought they would have done, and these are my strategies. So 511 minus 34. What I try to do is break it up because that's more easier for me. 511 minus 34.
So I think the camera goes in really closely at the moment. And she's kind of explaining what she's got written down here. And why or why not? And she makes this forms this lovely conjecture here, is because a 3-digit minus a 2-digit, that she's just got the little takeaway sign in there, a 2-digit cannot make a 2-digit number. So that's her reason for why this is not correct. And then on the left-hand side here, she's explaining the way she thinks that they did it. And this, we know, is a common misconception that students have with subtraction. And then on the right-hand side, she's done 2 ways in which she can show that this answer is incorrect, by verifying using one method and then checking it with another method to show that this is correct and to substantiate the claim that she made at the beginning. Okay, we'll go back to the slides, thanks. Another reason why is reasoning important, because it provides opportunities for both creative and critical thinking. So hopefully those 2 little illustrations showed on the one hand the creative ideas that young children can have, as well as the critical thinking that they can do. We know that this notion of creative and critical thinking has been talked about by the chief scientists. It's a general capability in the Australian curriculum, and Mr. Gonski now has said it's really important in the last couple of days. And so mathematical reasoning involves creative and critical thinking. And often when we think about this creative and critical thinking, we don't think that it's part of maths, but it actually is, and it's really central to mathematics. So, why is it important? Some other research that's been done by Staples with middle year students says that it enhances students' engagement in mathematics. They develop a positive disposition, lifelong skills, and it influences the social dynamics of the classroom. I thought this was really interesting, especially thinking about it being in the middle years classrooms, where the teachers talked about in their study, justification empowering students, which shifted the dynamics of the classroom so that the teacher was not the only one who knew. So we had a little bit of evidence of that, not to say that it didn't happen in that classroom, but we weren't collecting data about that, but I suspect that that's probably was certainly there, because we had students who were going home with some of our problems and doing the next what if part of it, and we were seeing that in the reflections that they were writing about the tasks at the end of the lesson. Our primary teachers' explanations about why reasoning is important and what they noticed about it, well, the kids were constantly having to explain because they worked in partners, which meant they could make their thinking out loud. You could always hear them justifying, thinking about the other reasons why things won't work or the reasons why things do work. And another teacher says they were connecting their understanding and their knowledge. They're bringing in all of their knowledge and they're putting it all together and figuring bigger things out through reasoning. And they also commented on the benefits of observing the demonstration lessons because that gave them an opportunity to really sit there or stand there and focus on what the students were doing in this time. And I thought it was fantastic to be able to take a step back and observe the conversations that the students were having, how they were going to convince each other about their numbers. So I think being able to observe that lesson allowed all of us to be able to tap into that conversation and hear it as it's happening, rather than getting a piece of work and then having to say afterwards, can you explain your reasoning behind this? And so I think that meant that teachers realised that they had to do a lot more observing in their classrooms and conversations with students as it was happening. And that came up later in our assessing reasoning work as well. We noticed these things in our analysis of what the students were doing, that there was a diversity of responses when students were given a reasoning task about the nature of the reasoning processes that they used and their capacity to use these different reasoning processes. For us, comparing and contrasting was a critical element of mathematical reasoning, both because it led to being able to generalise and also to be able to justify. And this was an element in the frameworks that published in papers and things that wasn't emphasised so much until Jeanette and Kieran came along and made a big deal of it. So we were happy that that was there in their work as well. There's a difference between explaining how and explaining why. And when you get into explaining why, that's when you're justifying. And at the beginning of our study, we think that the teachers who were talking about explaining as being reasoning, they were talking about explaining how. And so they discovered that difference. We also noticed that the students realised that justifying could be done in a few different ways. You could verify by confirming all cases, or you could refute by showing a counter-example, as we saw. And that there was a diversity in the way that the students communicated. So the idea of gesture was important for some students. There was verbal explanations and communication of their reasoning. Their students used diagrams, they used symbols, they used sentences, written sentences. Our primary teachers noticed the limitations in children's mathematical language because they realised that that was important for communicating these generalisations and these justifications that they were trying to make. They were often very focused on the oral communication rather than the other ways in which the students might have communicated. They were sensitive to the role that prior learning was playing, and so there were some teachers who wanted to go and teach all the ideas, so that would then come out when they were doing the investigation. Some were a bit less sensitive to the idea, to the way in which their students who were justifying were able to make sense of their prior knowledge. But many of our teachers noticed the importance of the questions and the prompts used by teachers to elicit students' reasoning, to support it and to challenge it. When we came to doing the next project, we realised that from our work we could identify 3 key ideas, and again these then matched up with Jeanette and Kieran's ideas, the idea of analysing, generalising and justifying. And often the tasks that we were giving students meant that they'd be doing a combination of 2 of these things. You have to analyse in order to generalise, you have to analyse in order to justify, and some of the tasks involved all 3 of these. So our definition that we used in this project on assessing mathematical reasoning was that analysing involves exploring the problem using examples provided or generating examples to form or test a conjecture. Generalising involves identifying common properties or patterns across more than one case and communicating a rule to describe the common property, pattern or relationship. And justifying involves checking the truth of conjectures and generalisation, and also involves using logical argument to convince others. So what does that look like in the classroom? So here's another problem that we did. Sharon's really familiar with this one. The magic V. You've got five numbers, 1 to 2, 3, 4 and 5, and they're arranged in this V, and you need to find some other magic Vs. And of course the discussion at the beginning of the lesson is what is a magic V, and a magic V is one where the sum of the numbers in each of the arms is the same. In this case, the sum on one side adds to 9 and the sum on the other arm adds to 9. And the students have to find some other magic Vs. How do you know it's a magic V? And what is the same and what is different about all the magic Vs that you find? So here's some students, and they were provided with the numbers that they can move around on the sheet. So we've got a response from Leo and Ben. And I think this is probably a Year 4 class. I didn't write that down. So we have only 4 magic Vs, and we just started to switch the numbers around to different positions. I could switch this 3 and the 2, and it would have been a different one. So they'd identified these ones, and then they thought they could do something else. So this is their process of analysing it. Was systematic in their search for examples. They were able to explain how they found other cases, and they were comparing and contrasting their examples as they were going. And the teacher prompts that we think that are important at this point is, how do you know when you found all the cases? And what happens if you try a 4 at the vertex? Or a 2. And then the next part of this lesson is all the students take up one of their magic Vs, and you put up a poster and you have a whole class discussion about comparing and contrasting all these magic Vs. You might notice something yourself as you're looking at this poster, which is one pair of students' work. Then the teacher has a discussion. So the generalising happens as part of the whole class discussion in this lesson. What do you notice about the magic V? One of the students says, all the numbers at the bottom are 1, 3 or 5. Okay. And then another girl said 1, 3 or 5 because those numbers, because they're all kind of special numbers. So that's another thing that we notice, that the students like to use a lot of metaphors. I think as teachers we use a lot of metaphors as well. And so it took a little bit more of a conversation there before we got to that, oh, they're odd numbers, aren't they? What are the odd? And so then the teacher is, so what's an odd number? And we've got, just before she asks that, a number that doesn't have a partner. So again, we've got another metaphor that students have been using in their words. So we've got some analysing happening here, and we've got some attempts to generalise using a metaphor, and then we've got communicating a rule in terms of they're all odd numbers, and the teacher asking another prompt to provoke explaining of what this conjecture is that they have. In the next part of the lesson, there's a formal conjecture there that says, Sam said it's impossible to make a magic V with an even number at the bottom and with a set of numbers 1 to 5. Is Sam right? Explain why or why not. So here we're focusing on the analysing and the justifying part of the lesson. And there's a couple of students out there talking about what they think in presenting to the class. So here are 3 different responses from pairs of students. One that says, we think that Sam is right because we've tried the 2 even numbers and none of them worked, and we mixed the numbers around and only the odd numbers worked. So they'd worked really hard doing this. So this is an idea, yes, they're attempting to verify by testing all the possibilities. But there's really no evidence that they've exhausted all the cases in what they've said. They've just said, we've just tried everything. The next pair says, I agree with Sam, you need 2 even numbers to make the even number, and you need 2 odds and 1 even to get the even number. So here we've got some students who are attempting to make a logical argument. They've got some ideas about what the properties of odd and even numbers are, but they're struggling to see how that understanding actually fits with the problem that they're doing. And then we've got a couple of students that say, if we select an even number to put at the vertex, the 4 digits remaining add to an odd total. Then it is not possible to divide equally by 2 to form 2 equivalent sums. So we've got some students who have used an if-then statement. It's a logical argument that they've made. Again, we might still want to use some prompts. Why does that matter? Why does it have to add to that? So part of our work then was taking all of these examples of different things and ways in which students analysed, generalised and justified to find some trajectory there. And these materials will be published on the Resolve website. I don't know what the due date is, but they're there for them to publish. Oh, right. Good on you. So here's a couple of other different generalising tasks that we've used or the teachers found for themselves to use during our project. One is the matchstick problem, where you're joining matchsticks together to make squares. How many do you need to make 8? How many do you need to make 100? What else belongs? This is one of the tasks we start with, 18, 12, 36. How do you know these numbers belong together? What is your reason? What other numbers might belong? Convince me. Teachers in our schools, instead of having those 3 numbers, they use fractions, decimals, a mixture of fractions and decimals. They were using a whole lot of things to explore the properties of number. And this other problem, the fortune slip, there was also a number towers problem. Again, it's about odd and even number properties, which is in the Year 4 maths curriculum. And the other one, the perimeter investigation, was one that the teacher decided to do with her students. How many different rectangular shapes can you make with a perimeter of 24 centimetres? What do you notice about the area of all of these shapes? So this was leading to that. And those students then used the geo board on their little smart boards and did their presentations about what they found. They got really excited. The other types of justifying tasks, as I said before, is it true? Let's justify. And we had set this problem of, Nathan said, whenever you increase the perimeter of a rectangle, the area also increases. Is Nathan correct? Explain why not? Again, these kinds of questions are really good for addressing common misconceptions that students have. 2/3 is less than 3/6. Of course it is. 2 is less than 3 and 3 is less than 6. 8/9 plus 1/10 is less than 1, is it? I don't know. 1/10's bigger than 9's. I don't know. So it's those kinds of things that you want students to explore. We've developed, to support teachers, a set of eliciting, supporting and challenging prompts to go along with each of these key reasoning ideas. So I'd like to conclude by hoping that I've demonstrated that teaching reasoning requires teachers to establish a classroom culture in which reasoning is expected, accepted and valued. And we think that reasoning should be included in almost all lessons. It is vital for developing mathematical understanding, and it provides opportunities for students to be creative and critical thinkers. So look for opportunities in existing lessons to promote reasoning. Use teacher prompts to elicit and challenge reasoning. Allow wait time for reasoning to occur, and search for and use tasks that provide these opportunities. I'd really like to acknowledge my colleagues from Deakin University. We worked on this for a number of years. Leisha Bragg, Sandra Herbert, Esther Lung, Monty Wajaja, and our own Ailey Davidson, who's one of our PhD students here, and Sharon Livy, who's now one of our academic staff, who also helped us out along the way. As I mentioned, we worked with 11 Victorian primary schools to do this work, one Canadian elementary school that came to 63 primary teachers that we want to thank very much, and all of their students. It's over to questions now.
And if you have a question, if you put your hand up, Reggie's got a microphone and we'll get around to you quickly.
Thanks, Colleen. It was really interesting, and especially for a non-specialist maths person myself engaging with some of these problems. You can see on our desk we were still trying to figure out the plastic cube problem here. But
good.
Yeah. One thing that's intriguing me is the distinction between creative and critical thinking. So, for instance, in the first video, you talked about that in being creative thinking, and the second video about critical thinking. So can you say something about how you distinguish between those kinds of thinking and then how that connects in with the idea of reasoning?
I think for me and our work, it comes back to, and I'm thinking about a quote from another mathematician from ages ago, but it's about when you have a conversation with somebody and about telling you about something, they might, and it's kind of a new idea for you, and you want to know more about it. And when a person just explains the whole story all over again, rather than giving you reasons or justifying, and providing an argument for why you should accept this idea or do this new thing that they think is wonderful, then I think that's when you're actually using and wanting people to demonstrate critical thinking, and you're demanding that they convince you, give you a reason. So for me, it's when that occurs in mathematics that's what I think the critical thinking is about, is being able to provide the argument for why something is true or why a conjecture doesn't hold. And for me, that's it's about being convincing. So that's what I think, for me, connects with the idea of critical thinking. I don't know what other people think, but that's what we've been interpreting it as.
Does that connect with creative thinking? Because that was the first example.
Well, a lot of people just jump to thinking about creative thinking as being problem solving. And that's what we need to do in maths. But in this case, when we're thinking about situations where we're wanting to notice what is the same and what is different, and we know that mathematics is all about trying to identify these common properties of numbers, of shapes, of relationships. And so when you're generating and noticing that for yourself, you are being creative. You're not being told, oh, don't you notice this relationship? Haven't you noticed that they've got parallel lines, these shapes? It's that you want the students themselves to notice those things.
Thank you. Have you thought about what this research might look like if you were to undertake it in secondary schools?
We have, and we'd love somebody here who's from a secondary school to say, come and do some work with us.
What do you think would happen when you're sort of competing against, some of the ideas of, having to solve algorithms and, just get the right answer, and the pressures that exist as you sort of, get towards year 10, year 11 and 12 for searching for the answer, not necessarily.
I think that there are still lots of opportunities in mathematics classes and in secondary classrooms to not just go with telling in the first instance, even with them quite simple things like where do the index laws come from. Students can find them for themselves really quite easily. What does a to the -6 mean, and how would you find it? And they can use pattern and so on to do that. And that's only a small part of a lesson. It's not like it's going to take up 3 periods or something like that. And in terms of the justifying part, if we allow students in some of those situations, and we've just got to turn the problems around a bit and expect them to justify and explain and explain why, then I think it's a way of opening up other opportunities. So we haven't done the work in secondary schools, so I'm just hypothesising. And I know, and even for primary teachers, there's a whole pressure on getting through the curriculum, getting through the topics. But we also know that leaves some students behind, and that understanding is really an important proficiency. And we've kind of come to understand the fact that all of those proficiencies really are entwined, and you need each one of them in order to be effective at one of the others.
And can I have a second question?
Okay, go for it. I'll come back to you in a minute, Pat.
With programs like Choose Maths, which is, you know, targeting girls to engage more in mathematics, did you notice anything in the research that you've done in terms of how boys and girls respond or engage with this, with the sort of mathematical reasoning that you were presenting the students with?
We didn't do an explicit gender analysis of that, but we could. And I just say that both boys and girls were excited by the tasks, and without knowing a lot more about the individual students, I probably jumped to some conclusions. So some girls found it easier to explain than other girls, and some boys found it easy to communicate their ideas than other boys. What teachers were surprised about was that some students got really excited and involved in the task, and they were surprised that those students were expressing some of those ideas, whereas some of the others who were focused on recall and repetitive things, they just wanted to get on with the next task rather than think about explaining why and justifying. Okay.
I was thinking about the idea of creative and critical thinking as a doing thing, and them applying themselves in mathematical classes in doing and solving problems.
Yeah.
Did you, in part of your studies, see any translating of those problem-solving, doing things into other areas, like maybe English or something completely different? Not science, no. English or humanities, like in history or something like that?
No, we didn't do any of that, any of those kinds of things with the tasks that we had. But what I didn't mention before is that the teachers realised how important the mathematical vocabulary and the symbols were in students being able to be more successfully write a rule or communicate a rule or justify or to put together a logical argument. And that, yes, metaphors were useful, but that they needed to go beyond that. So that was a big learning idea for some students. So the connection there between language and mathematics and the capacity to reasoning was really strong for some teachers.
Colleen. Hi, Colleen.
Oh, hi.
Yeah. We've had a lot of live streamers on. Sorry to interrupt.
Yeah.
We've got a lot of live streamers asking a few questions. So I'm going to just throw one of the questions from Selena, who's online with us.
Hey, Selena.
Selena is asking if you have examples of teaching and assessment of reasoning in a secondary classroom.
No, we don't. But we'd love to come to Selena's classroom and do some work with her.
Thank you, Colleen. I thought that was really interesting. And even though we couldn't hear the video, one of the things that I think you made the point really strongly was that pupil talk can actually address curriculum requirements if you allow that talk to happen. What I wanted to ask you actually relates to, I think, one of the early questions, and it's about insight. In the video of the two boys with the cube, the boy who kind of explained the, a formula generated a statement, actually knew, he could see what was happening. And I wonder if you could comment on that insight, how that kind of connects with, when you just know, and then how you move into justifying from there.
I'm not sure that I can really comment on this particular student because I wasn't in this I was in this classroom. Yeah, I know in general. But from other things that we've done, it does mean that they move through a few steps in order to get to that statement. They don't just get to that end statement that he said, oh, it's n minus 1 was, and then minus another 1, and then there's 6. They've actually started to realise that there's a pattern, but they're also using their spatial understanding and their understanding of shape, in this case, to start thinking in that way, because they needed that idea to do the number of cubes that are have one side painted, but they were using other ideas to come up with what's the rule for 2 sides painted and what's the rule for 3 sides painted. And other students in the class were noticing the patterns because they had drawn up tables to be able to record what their answers were, because they were calculating them by counting, and then they were starting to notice the pattern. This pair of students didn't need to do all of that because they'd started to use their knowledge and spatial understanding and started to try and figure out a way of explaining the rule that they saw for themselves as evident. So I don't know that I've answered your question, Pat, but yeah, but it's... So again, we've theorised this learning trajectory about students moving from being able to do one thing to another thing, but it's really important that teachers have a set of questions ready to be able to move them up to the next deeper level of reasoning, whether it's generalising or justifying, and it's the questions that you ask that help them to make the next step. Another one from
Online.
Online.
Yep. We've got Kathy, who I think we know at Monash. She's asking, did teachers comment about the changes this focus demanded of their teaching practice? What challenges did it present for them?
Well, yes, that's certainly came up, and Sandra and Alicia, who then went on and did a study around what it meant for planning things. They probably can talk a bit more about it. But within our assessing project, they did kind of articulate the problem of how we needed to do the formative assessment, and they realised that the best way of doing that was to be there on the spot with the students as they were doing things, rather than asking the questions later and, you know, just working from what was left on the worksheet at the end. And so that was one of the challenges for teachers, to be able to do that and to think about how they would get to find out about all of the students in their class, because they obviously can't be there standing observing every student for every minute of the class. So they did talk about particular strategies and how they might do that, and how we might think about how to support them with that. So any ideas from you people about how to do that would be really good. Yep. Yes, person. I need a clock in here. I've got no idea what time it is.
5 to 8. If you're essentially using the 5 E's and Maslow's hierarchy of needs, is there a justification for why you are asking students to analyse and justify and, I am sorry, I've completely... Generalise.
Yeah. Only because we're just trying to make a connection with mathematics and make it sense within the mathematics discipline of those things. So if you can see the connections between those doing words and the Maslow's hierarchy, that's great, because then you've got an idea of really what it might look like in a mathematics classroom.
Okay, maybe one more. The microphone has it.
Colleen, Janine.
Yes. Hi, Janine.
From way back. Actually, in fact, I went to the alcoholic lecture at MAV in about 19...
Oh, really? When I did that about that?
I'm trying to think, but...
About how much alcohol
wonderful thing.
Men and women
as we were drinking tonight.
Yeah.
But that's not my question. Actually, my question is a bit global, but when you were talking about reasoning and developing these skills, which we actually ran a similar thing at the CEO today, with the capabilities on critical thinking and what's important for teachers to be developing the questions, the
Are we
analysis.
on the same plane?
Yeah, so we are. My issue is, though, that now we've got to be radical, like Malcolm Turnbull. Reasoning we don't do for the sake of mathematical reasoning. We've got to have a bigger cause. What does Elon Musk need to actually get us to Mars? Like, for me, the challenges for kids, and we're not getting them into specialist maths now, the challenge for us is to see how this reasoning develops into something that's really important for our development. Dare I mention the dreaded word STEM, but the fact is that we need to connect. Do you see how to do that with the maths? Like, you've done the maths research out there. What's your next step, though? For me, in terms of developing this, it's very important. Where do you see it going in the light of the world's changing dramatically? I think it's very exciting, but just how do you see it evolving? Because I know John would like to know. Anyone can answer it.
Any ideas? I think it is a challenge for me. What I'm noticing is the idea in which reasoning is bound up with understanding and fluency and being able to problem solve. So I think they do. I really do support Kilpatrick and all those other people who have said about those things being entwined, and that it's when students make sense of mathematics. And when students experience the joy of discovering something, which is what Stacey talks about mostly, that's when they get inspired. They want to take home the problem like the magic V and says, well, what happens if we use the numbers 2, 3, 4, 5 and 6 instead of 1, 2, 3, 4 and 5? And they just spend, we had students, one of the teachers telling us they came back with all these ideas and then they wanted to do 3, 4, 5, 6, 8, And so that's what you want the students to be thinking about, and they're the skills that really are about the creative and critical thinking, the creative thinking about what if, and it's just in the mathematics context, and we're not expecting the teachers to be able to do what ifs about anything else, but just to sort of keep it focused. And we know while the students are doing that exploration for themselves, they're deepening their understanding of mathematics, and they're developing the skills in logical argument around that.
Okay, so I'm going to pull this to a conclusion, although I know there are lots more questions going around and you can grab Colleen later. But here's something that is so typical of what happens when you think about teaching and learning, that ideas trigger thinking about resources, possibilities, and where things go to next. So our last question is not a question, but is an explanation and a statement.
So I'm Jenny and I'm actually doing the Resolve Champions program, so that's why I've been on. So I would like to suggest that you all get onto Resolve Inquiry Mathematics. It's an Australian site sponsored by the federal government, and they're trying to train up champions so that we can change this thinking of mathematics. So if you get onto that site, go into special topics, and in special topics there's a Year to 3, 6 assessing reasoning trial, and in there is everything that Kay has put up there. There are different coloured sheets and it's got questions that you can laminate. I've got them laminated with the things behind in my classroom, so you can use those questions to say, convince me this, is this true, or whatever. So you've got the resources at hand. There's assessments so that you can see where they are on that climbing thing, whatever, but it's fantastic. There's ideas of the Magic V I tried with the staff when I was doing this, but there's lots of other resources that it suggests for you to try just to be getting started.
Thank you. That's the way to go.
Okay, so just closing, Colleen, on my desk over there, I did a little bit of scribbling. I tried to do the Magic V. And, one of the things that's unusual about being a learner again is how frustrated you get when you can't do something. So you could go and look at my table later, but I have rubbed out the errors.
You needed to be working in pairs, John.
I needed to be in pairs. I needed someone who knew what to do.
You needed to have the conversation as you were struggling with moving the numbers around.
I was really struggling, and what it made me think was how many people of our generation grew up on learning how to use an algorithm, and that was all that mattered in mathematics. And so you start thinking about where are we moving in the future. You start to think about the arguments that are coming out now, and Gonski's certainly making today about individualised learning and paying attention to things beyond the propositional knowledge or the use of an algorithm. It is a challenge because there's a large amount of the population that don't understand why these things are important because they've never experienced it. And so, Colleen, one of the most important things about tonight is reminding all of us that the doing matters, but actually researching what happens and why it counts. The significance of the work is a really big deal, and that's the type of thing that an academic brings to bear on these things that really matters. And as you demonstrated tonight, Colleen, that's at the heart of your work. We are very grateful for you sharing with us tonight. Thank you very much.
Thank you. Thanks everyone for coming, it was great.